Okay, we're gonna continue on here. Last time we got into stoichiometry, I believe, and we talked about basic stoichiometry problems. We also talked about limiting reagent type problems. Remember, if you have a basic stoichiometry problem, there really is sort of 4 steps. You could balance the equation. You want to take whatever they give you and convert it to moles. You want to do the mole to mole relationship from the equation, which obviously is the stoichiometry part of it. Remember that stoichiometry really is just a conversion factor that you get from the balanced equation rather than looking it up somewhere like in a table. And lastly, you should always be in moles after that step, and you can convert it to some other unit. What makes something sort of a basic stoichiometry problem is really you're just given one piece of information about somebody in the equation. So maybe you have some information about a product, maybe you have some information about a reactant, and you just have one piece of information. And that's different than a limiting reagent type problem. In a limiting reagent type problem, the way that you, again, sort of know that it is a limiting reagent is that you can pretty much get to moles both of your reactants. So with the information given to you, you pretty much simply can convert those values into moles. And that is going to tell you that it is going to be a limiting reagent problem, which means, again, you do need to calculation wise determine which one is the limiting reagent. Now, the importance of the limiting reagent, like we talked about, is the limiting reagent or limiting reactant is the reactant that pretty much gets used up first in the chemical reaction. The other reactant is what's known as the excess reagent. And that one you have plenty of, and you'll still have some left over when the reaction's done. We talked about really 3 ways, but we did 2 ways of how you could do these type of problems. One way is basically our sort of 4 steps above, but halfway through, you need to do a limiting reagent calculation to determine which of those guys are the limiting reagent. In this sort of method, like we talked about, essentially, you're just going to do a very simple calculation between the 2 reactants, and you're going to figure out if you want to use up all of one of the reactants, how much of the other one would you need? And when you figure out how much you would need, you would compare it to how much you started with of that reactant. And if you did have enough, it would be the excess reagent. If you compare it to your starting amount and you did not have enough, then it would be your limiting reagent. Once you determine the limiting reagent, obviously that is what you want to use for the rest of the steps in that case. And we demonstrated doing it that way. Also, we talked about, and I might have demonstrated the other way, I don't remember, but the other way is very commonly taught is just to do 2 separate stoichiometry calculations, one starting with one reactant to the product that you're looking at, and then do a separate stoichiometry calculation with the other reactant to the product. And whichever one basically produces the least amount of product would be your limiting reagent and also your uh, theoretical yield. The way we also focused in on was perhaps a new sort of way for a lot of people, which is sort of an ice table approach. And in that ice table approach, again, the benefit of it, as we sort of talked about, is you essentially can very quickly pretty much figure out everything that you might ever be asked in a sort of limiting reagent type problem by doing this ice table. So, if you had something like this, you would start with the initial moles of each of these guys and zero out that guy. We would have a change, which is ultimately what we're finding, which is this would be minus 2x. Remember that you do need to use the coefficient, and that's because that is what does the mole to mole relationship. It does really the stoichiometry part of it for you. And this would be minus 3x again because of the coefficient. On this side, we would have plus 2x. What we would do is we would take our moles minus 2x down, our moles minus 3x down, and 2x. At this point, obviously, you would set each of these equal to 0, which is usually a fairly quick calculation, and you would solve for x for each of them. And whichever x gives you the smallest value, that would be your limiting reagent. So we'll just say this guy was the smallest value of x. That would mean you don't really need this value. And that x, though, is important because it's pretty much every x in here. And that would give you basically the moles of everybody very quickly. And then with some molar masses, you could pretty much calculate if you had two products, you know how much of each product you would get. Also, again, a very common calculation is how much of your excess reagents left over, so you can pop it back in there. And again, without necessarily having to go all the way back to the beginning, maybe and restart a calculation, you can just kind of jump in right there and really calculate everything that you would need. So remember that if you're going to do an ice table, probably it should be really only used in a limiting reagent type situation. If it's just a basic stoichiometry problem, I would roll with just the 4 steps like we did on the number of examples, and that would probably be the best approach. We tie that to percent yield, which again is our actual yield divided by our theoretical yield times 100%. The actual yield usually in book problems is given to you. So somewhere in the problem, they'll tell you how much you produced. And the theoretical is a calculation based off of the equation. Again, it could be a basic stoichiometry problem, it could be a limiting reagent type problem, but it's some type of calculation that you do basically with those steps there. Divide the two gets you to percent yield. We do want a relatively high percent yield, but not over 100. And again, that's usually not a good thing. Towards the end there, we got into solutions. And remember that solutions are the guys that have the aqueous symbol next to them. They are homogeneous mixtures. And there's really 2 parts to a solution. There's the solute, which is the smaller part. And there is the solvent, which is the larger part. And typically, we dissolve the solute in the solvent. And again, water oftentimes is a solvent, but as we talked about, I think last time as well, water is not always the best solvent for everything. It works really well for ionic things and things that are polar because water itself is polar. So it's able to interact with those other things pretty much the same way water is able to interact with itself. And that makes for things mixing really, really well. When you try to use something like water on something that's non-polar, they're going to try to use very different ways of interacting with each other, and they're not going to be able to really maintain that interaction over a long period of time. For example, non-polar things will use dispersion forces, which are very weak intermolecular forces, the way they interact with other molecules, while something like water is going to use hydrogen bonding, which is a relatively strong sort of intermolecular force. So over the long period of time, they just really can't keep it together pretty much. And although they may be able to mix shortly for a little bit of time, they will eventually sort of separate out and really can't mix. Now, we talked about concentration, and really molarity there is our big unit of concentration. And molarity is really moles of solute over liters of solution. It is really a formula. Molarity is moles per liter. We do solve really for any of these 3 options here. So liters is equal to moles divided by the molarity, and moles is equal to liters times molarity. So I would say we pretty much use this formula or equation for all 3 things. Very commonly liters and also very commonly moles is used a lot. When you do have a solution that is 4.5 molar, say again, sodium chloride, basically what that means is you have 4.50 moles of sodium chloride per liter. And again, I would highly recommend, like I talked about last time, if you're doing a calculation that involves molarity, I would take out the big M and replace it with moles per liter. Once again, it should always be 1 liter, and moles obviously is where the number stays with. I would also, like I mentioned before, is kind of do more of like a dimensional analysis, especially if you have molarity involved, and just think of it really as a conversion factor. As I mentioned before, if you sort of do a dimensional analysis, if you have the molarity given to you, it really will just sort of do the math for you if you're kind of popping into any of those equations by just doing opposites sort of cancel. What usually happens with a lot of people is they will leave the big M, as I mentioned last time, and pretty much all they think about is moles. They don't have any idea about the volume, where it is, what they should do with it. So that's, again, a very, very common sort of error. Now, we can use this obviously to calculate things like grams, and if we can figure out the moles for a particular molarity. As the molarity increases, so does the strength of that thing. So something with a very high molarity is very concentrated, and that's because the only way to get a high number is you have a lot of stuff on top. That means you have a lot of stuff floating around in the actual solution, which is the solute particles. When you have a lower molarity, then you have a little, not as much there up on top, so you don't have as much floating around in the solution, and it's more of a dilute solution. Any questions on any of that there? Okay. Speaking of molarity, before we get to that, let's also talk about how concentration works with basically ions. So, for example, if I had a 2 molar solution of sodium chloride, what that essentially means is, again, I have basically 2 moles per liter of sodium chloride. But if I want to know in a solution of sodium chloride, what was the concentrations of the actual ions that are floating around? So a reminder that a ionic compound like this is actually a strong electrolyte, which means when you make a solution of sodium chloride, you no longer have any sodium and chlorine units still together. They're just all going to basically break apart. What actually happens is the water molecules surround both of those ions and helps it dissolve, and they're basically floating around in the solution part of it. So sometimes we are interested in maybe not the entire ionic compound in terms of the concentration, but maybe we're interested in just like one of the ions or both of the ions. So the way molarity works pretty much is, if I know that the molarity of the whole thing here is 2 molar, when I look at this sort of sodium chloride and see how it breaks apart, I could see that it breaks apart into basically a 1-to-1 relationship between the whole thing and the sodium ions, which means if I wanted the concentration of the sodium ions, it would actually be 1 times 2 molar, which would give us 2 molar for our sodium ions. Same thing if I looked at the chloride, it's a 1-to-1 relationship between those two, which means if I was interested in just the concentration of the chloride, we would also do 1 times 2 molar, which would give us 2 molar chloride in this case. Now, if I have the same sort of 2 molar solution of calcium chloride, when calcium chloride breaks apart, we will get a calcium ion floating around, and we will actually get a couple of the chloride ions that will float around, as that's what the 2 on the bottom basically means. So when we look at the concentration of the calcium ions, it is a 1-to-1 relationship, which means it is 2 molar times 1, which is still 2 molar for our calcium ions. But when we look at the whole thing to the chloride, it is a 1-to-2 relationship, which means in order to get the concentration of the chloride, I would need to multiply the chloride's concentration by 2, basically, or the whole thing by 2. And that would give us basically that it is 4 molar chloride ions basically floating around. Concentration is not additive, so 2 and 4 doesn't give you 2. But it's sort of the proportion of what you get. If you just think about it logically, when sodium chloride goes into the solution, you get a 1-to-1 relationship basically of ions that go into that solution. So it's basically equally concentrated in both of those ions. But in the case of calcium chloride here, you actually get a 1-to-2 relationship. So you get twice as much chloride ions as you do calcium. So chloride is twice the concentration in that solution as the calcium ions are. That is the quick way that you can basically relate concentration from the entire ionic compound into the individual ions. You can do it really the long calculation just to show you how we actually get there. If we started with our 2 molar, which is moles of calcium chloride per liter, And basically what we did is if we look at the calcium, it's a 1 mole to 1 mole relationship. So 1 mole of the calcium chloride gives me 1 mole of just the calcium ions. The moles of the calcium ions cancel out, and I end up with 2 moles per liter of calcium ions. If I do that for my chloride, I will have 2 moles of calcium chloride per liter. It is again a 1 mole to 2 mole relationship, like we did stoichiometry basically. And that would give us 1 mole of our calcium chloride, gives us our 2 moles of chloride ions. They cancel, and that gives us our 4 moles per liter of chloride ions. That is essentially where we get this from, which is actually, we'll go here. Do that. We basically multiplied by 1, which is why we multiplied by 1. We basically multiplied by 2, which is why we multiplied by 2 there. So the top one is the shortcut way without doing the kind of stoichiometry or way of it. You basically, whatever the coefficient is in front of the ion, you would multiply the concentration you have for the entire ionic compound, and that will give you the concentration of just the ions. Any questions on that there? So again, like I said, sometimes we may just be interested in the ions concentration. So why don't you try that? So for each of these solutions, what is the concentration of each of the ions that Okay, so let's take a look. We'll take a look at the first one here. So again, you might want to think about how it's going to break apart in that solution. So if we have some sodium sulfate, you are going to get a couple of sodium ions floating around in that solution, and you'll get a sulfate ion basically floating around. And here we do know the concentration basically is 1.2 molar. So again, we could just basically kind of do like a stoichiometry. It's a 1 to 2 relationship. So for the sodium ions, we would need to take 2 times that concentration. And that would give us 2.4 molar for our sodium ions. When we look at the sulfate, is a 1 to 1 relationship. So basically, we're taking 1 times the 1.2 molar, and that's going to give us 1.2 molar for our sulfate. Again, when that thing drops into the solution, you got twice the amount of sodium for every sulfate that goes in there, twice as concentrated in sodium ions as it is in sulfate ions, basically in this case. Any questions on that one there? Looking at the second one there, that's potassium chromate. Also, when it goes for a little swim, it's going to make a couple of potassium ions and a chromate ion here. Again, we could apply the same sort of logic here. It's going to be a 1 to 2 relationship for our potassium. So we do need to multiply that guy by 2 to get the proper concentration. 1.5 molar potassium. It is, though, a 1 to 1 relationship between the whole thing and the chromate. So we'll just multiply by 1 or basically keep the same concentration. Going to give us 0.75 molar chromate in this case. Any questions on how to get concentrations of ions? Obviously, if you have the concentration of ion or molarity of the ion, you could figure out other things like obviously how many moles, volumes, those type of things that's going on with the molarity equation. Any questions on molarity? Yeah. Yeah.
If I write it down when it's test, I write a 1.5 but not a 0, like lose my point.
No, in this case, I think the original concentration was 3 significant figures, so 1.50 would have 3. So you probably wouldn't necessarily need the extra 0 on that one. Yeah. Yep. Other questions? Because ultimately, even though I guess it was what we did, we basically multiplied there, so we would be looking at more significant figures. Yeah. Other questions? Okay, then let's continue on here. So if you're going to make a solution of a known molarity like we're going to do in like an hour and a half or so, yeah, You could take something like this volumetric flask right here. By the way, the volumetric flask has one marking, and that is the marking for this particular guy. Well, let's just say it's 250 milliliters, like later today. By the way, volumetric also means you go 2 decimal places when you're recording that volume. So typically you put a little bit of the solid in your volumetric flask, or you might want to do a little pre-dissolving in a beaker. Obviously, if you don't go over 250 milliliters of water when you're dissolving it, you should be in good shape. Add a little bit of water. You typically want to go to about there with some of the water, put the cap back on and start shaking to start dissolving. You typically do not want to bring the water into the neck of the volumetric flask until you pretty much have it all dissolved. Otherwise, there's really not enough room to kind of get everything to dissolve if it's not. So that's why sometimes pre-dissolving a little bit in a beaker, then pouring it in there also prevents clogging of the funnel when you just pour a bunch of solid in there and it gets clogged. That will allow it to kind of dissolve a little bit better. So you'll fill it up to the meniscus, obviously, here at the line, and that again should give you a solution that has a certain volume. Now, let's just say you're doing this like later today. What you want to do is once you get it dissolved, and you may have to continue to add water. I don't know why my water is green now, but you need to add some water here a little bit more to get it to dissolve. Again, hopefully you will have it dissolve before you get up into that neck. When you add the water, the neck is very thin versus the wider part on the bottom, which means when you add water there, it's going to go up very quickly. Yes. So you want to add water really slow, say something like a wash bottle, right? Because you want to make sure you could really stop it, even maybe a medicine dropper as you get really close. Because you wouldn't want to be the person that did this. Yes, I just missed the line by a little, right? Can I just pour out the top part and bring it back to the line? I cannot because I already dissolved that, right? There goes my solute out with the water, right? So you would have to dump it out technically and start again. Yeah. So just a cautionary tale for later on, go super slow. Yes. And make sure you don't go over the line so you don't have to keep making the solution. All right. So let's talk about dilution. And dilution is a process that is used to prepare basically a less concentrated solution from a more concentrated solution. Typically speaking, the way you usually buy solutions, for example, is they're usually more concentrated. And then they take those solutions, they dilute it down, and they basically, that's what we use, say, in the laboratory in most cases. And when we do a dilution, really the only thing that we add is more solvent. So we usually just add more solvent. A lot of people say you just add more water, which again, water is a solvent for a lot of things, but not always a solvent. But technically speaking, you're adding more solvent. That means that the moles that you started with will still be there, and the moles after you dilute it with some more water will still be there. They will not change. By the way, when you do a reaction that involves a solution, the thing that's reacting is the solute particles or molecules there are ions that are floating around that solution. That's the stuff that's actually reacting when something reacts with that particular solution. So what happens is when you do a dilution, because molarity is moles of solute divided by liters of solution, and as we talked about earlier, solution is both the solute plus the solvent. When you do a dilution, the only thing that you're technically adding to it is you're increasing the bottom number there, the liters of solution, which means the bottom number here gets larger. And because the bottom number gets larger, the molarity goes down, right? So it gets smaller on the overall the molarity because you're increasing basically the liters of solution, and that brings the molarity down. So there is an equation that you could use to solve for a dilution, and this is the equation here. And I would say most people roll with this equation, which is basically M1 V1 equals M2 V2. This is really the dilution equation. And the reason most people use this is the most common unit of concentration is molarity. So very commonly people use that. I will say that nowadays books and stuff will use C1V1 equals C2V2, where C is just concentration. And it really can be any unit of concentration you want. It doesn't have to be molarity on both sides. It could be something like percent mass to mass, percent mass to volume, some other concentration unit. But again, most of the time you're dealing with molarity. So a lot of times people just use the M1V1 equals M2V2. But if you like C1V1 equals C2V2, go for it. Typically speaking, the ones here are your more concentrated, and the twos are your more dilute. It really doesn't matter as long as you keep the numbers that go together on one side versus the other. So a couple of things about this equation. First thing is this. If you are using molarity by itself in a non-dilution situation like we have going on and we're talking about here, if you're just using molarity by itself and you're using volume, you should 100% of the time convert the volume into liters so that when you multiply it by the molarity, you will get moles, which is probably what you're looking for. Now, if you are using this dilution equation, you could leave the volume in milliliters. It's all good. It will work out as long as the milliliters are on both sides. Or if you have milliliters for one volume and you're solving for the other volume, it'll be in milliliters. The reason for that is this. If you're going to solve, for example, for M2, M2 would be M1, V1, and V2. And if we did molarity, milliliters on top and milliliters on the bottom, they will cancel and you'll be back to molarity. So it's all good to go if you want to do that. Again, as we talked about last time, if you multiply milliliters times molarity, you get millimoles, not just moles, but millimoles. So that's why if you divide it by milliliters, you get molarity back. So you can leave it in milliliters if you want. If you want to convert it to liters, you could do that as well. The only difference is when you solve for volume, you will be solving for liters when you do that. It works as well if you're solving for volume. So if you're solving for V2, it would equal M1, V1, and M2. The molarities will cancel. So if your V2 was in milliliters or V1 was in milliliters, your V2 will be in milliliters as well. So if you don't want to convert it to liters, you don't have to if you're using this equation. If you're not using this equation, you're just using molarity by itself with volume, convert it to liters so you get the right answer. Yeah? Any questions on that? This equation should really only be used in a dilution situation. Now, if you Google it or look around, sometimes people will go, hey, that's your titration equation. And the answer is only in a very specific type of titration will that give you the right answer when you have a one-to-one relationship. If you have a different relationship between the acid and base and you try to use that in a titration situation, you'll get the wrong answer because you'll have the wrong stoichiometry and mole-to-mole relationship. My recommendation is use it only in dilution situations. If you're going to do some type of titration calculation, which we'll talk about shortly, just do the calculation stoichiometry and you'll get the right answer all the time. But sometimes people will call that the titration equation. I personally would probably not use it in that situation. All right, so why don't you try this one here? How would you prepare 60 milliliters of a 0.2 molar nitric acid solution from a 4 molar nitric acid solution? So basically what we got going on here is we have a bottle sitting here that is 4 molar nitric acid. And eventually here we want to make another container that has a volume of 60 milliliters. And we'll end up with a molarity of 0.2 molar. So it's definitely a dilution. We basically are trying to make a lower concentrated nitric acid from a higher concentrated one. So we could use our M1 V1 equals M2 V2. Again, it really doesn't matter which ones you call what, but typically the more concentrated ones are the ones. So here M1 would be 4 molar We don't have V1 that goes with it. We do have our desired molarity, which is the less concentrated of a 0.2 molar. And we do have the volume that we want to make, which is 60 milliliters. So in this case, we're actually going to solve for V1. We're going to divide M1 to the other side. And that's going to give us V1 is equal to M2 V2 M1. Putting our numbers in there, we'll get 0.2 molar. We'll have 60 milliliters. Once again here, as I just was talking about, I really don't need to convert it to liters, but if you want to, you definitely can if you choose to do so. We'll divide it here by 4 molar. This is again why I do not necessarily have to convert it to liters in this case, because the molarities will cancel and I'll be left with milliliters. And if I do that, that's a 0.2 times a 60, hey, divided by not a 2, but a 4. And that's going to give me here 3 milliliters. So what is that 3 milliliters of? That's actually 3 milliliters of the 4 molar nitric acid. That basically means I need to come into this bottle that's more concentrated and take out 3 milliliters there of it. Now, I do want to end up here with my final concentration or my final volume of 60 milliliters. So should I add 60 milliliters of water in with that? I should not, because if I added 60 milliliters of water in there, I will now have 63 milliliters, which is too much volume, right? And that will affect the molarity I'm trying to make. So if we wanted to figure out, for example, the volume of water that you need, typically speaking, if you do more concentrated on one and less concentrated on two, V2 minus V1 will tell you basically how much water you should throw in there. We want to end up at 60, and we already tossed in there 3. So I can go with no calculator on this one. 57, I hope, milliliters of water would be needed. So we would top this guy off with about 57 milliliters of deionized water in most cases. And at that point, if I give it a mixy, shaky, maybe not so much shaky, but a little mixy. I will then have a total volume of 60 milliliters, and that solution should have this concentration of 0.2 molar. Any questions on that? So that's also a very common thing people do when they make a solution is they just see that like final volume and they just add that much water to what they already added. And again, they actually end up with a concentration that's less than, what they're shooting for in that case. Any questions on that there? All right, try one more here. See what you come up with. What volume of water is needed to prepare 500 milliliters of a 0.25? Okay, so again, similar idea here is a dilution. So once again, we have a bottle, the more concentrated 5 molar in this case, calcium nitrate. We are eventually want to make a solution that again has a total volume here of 500 milliliters and a molarity of 0.25 molar. So here our M1 will be our more concentrated, which is 5. Our V1 we do not have. Our M2 would be the less concentrated, and the V2 would be the volume that we want to make of it. So again, here we're going to solve for V1. So that's going to give us V1 is equal to M2 V2 divided by M1. Once again here, I do not need to convert to liters because I'm using this formula. So if you do, you're more than welcome to do so, but you did not have to. And try to squeeze my 500 milliliters in there. Divided by my 5 molar. Molarities will cancel, and that's going to get me there 0.25 times 500 divided by 5. And we're going to end up with 25 milliliters. Again, that is 25 milliliters of the 5 molar calcium nitrate solution, the more concentrated solution. So once again, we're going to take out of here 25 milliliters of the more concentrated one. That means that I can figure out how much water I need again by taking my V2 minus V1. So I want to end up at 500 milliliters. I've already tossed in there 25 milliliters of solution. that is a net of like 475 milliliters of water needs to go into there with it. And once again, you mix it up, and that is this concentration and volume of the solution you should have. So it's really important when you're doing dilution problems that you actually read the question carefully, because I would say more times than not, the question will ask you something like that, like how much solvent, how much water do you need to add, how would you prepare it? Again, if you solve for M1, that is the concentration usually of the more concentrated solution. V1 is the volume of that more concentrated solution you need. M2 is typically concentration of the more dilute solution. And V2 is usually your total volume of this dilute solution you're trying to make. Any questions on dilution? Yeah. Yeah, I would say not all the time, but in the context of this, it would really what's going to tell you that it is a dilution is when you look at what's being involved. We basically have calcium nitrate and we have calcium nitrate. There's nothing else sort of happening. And we just have two different molarities of the same thing. And if one of those molarities is greater than the other, then it's most likely going to be a dilution problem. So I would say you would probably be okay in a lot of calculations if you just kind of did that, but not all calculations you would be okay in. So really that's what you want to look at is like it's really not reacting with anything else. There's no other like formula, but it's just like the same formula, but they're different sort of concentrations. That's usually a very good sign that's going to be a dilution problem. Other questions? All right, so then let's get into some other stuff here. Now, we could do stoichiometry problems like we've been doing, sort of basic stoichiometry problems, our limiting reagent type stoichiometry problems. And one way in the laboratory that sort of comes into play is a procedure that we actually don't do in this class, which is known as gravimetric analysis. And gravimetric analysis is usually a situation where you make a precipitate, you do like a precipitation reaction, double displacement reaction, mix a couple of solutions together, and you can see a solid being formed right there. And you're interested really in how much solid that you would make. So we would filter the solid, and that's what's happening here. This is actually vacuum filtration. They hook it up to a vacuum line, which you've ever wondered why there's vacuum lines in the lab. That's what it's usually used for. And it will basically suck everything out really quickly, and your filtering is done in a second, rather than normally how we filter things these days, which is by gravity, basically, right? Put a funnel and a filter paper and just let gravity do its thing, basically to do it. They don't let you use that because, those are quite expensive things. Sometimes those Buchner funnels is what those are called, and a Buchner flask. And so after they broke them for all these years, they decided just let them do gravity, let the thing just filter by itself. But what you would do in this case, obviously, is that's going to suck out all the liquid. On the filter paper would be all the solid that you made, right? And you could reweigh it at the end once it's dry and everything. And this would give you your actual yield, for example. You could do a stoichiometry calculation like we did previously, knowing how much you started with, maybe of one of the reactants, the limiting reagent reactant, and you could calculate the theoretical yield. And then obviously you could get to your percent yield like we were talking about. This is a very common procedure in the laboratory where people get over 100% yield. And that is because when they do the filtering part here, that is all wet, that filter paper, and they don't let it dry completely. And so what happens is they reweigh it, and now they have water weight counting for product that they made, which they really didn't make. And now they have like 140% yield or like 400% yield, like I saw the other day in a lab, basically. They had like 190% yield, I think. So that's a very common sort of error that happens in this type of experiment. Now, another type of sort of one, obviously, as I just talked about there, you could use stoichiometry in these type of experiments. Another one that we could do stoichiometry with is titrations, like we're going to do today and all of next week, nonstop titrations, which is also going to involve really Stoichiometry is going to be basically what's sometimes referred to as solution stoichiometry. And you could use stoichiometry to do calculations. And typically when we do a titration like you're going to do later today, we typically have one solution that is sometimes referred to as the known solution. And the known solution is pretty much like it sounds. You know what the molarity is, you know how much of it did you use, you kind of know everything about that particular solution. You typically will also have another solution that you're using in the titration, which is sometimes considered the unknown solution. And there's something about that solution that you don't know. It could be the molarity of that solution. It could be like the molar mass of that solution. It could be the equivalent mass of that solution. It could be a whole bunch of things about that solution you don't know. Perhaps the only thing that you know about that solution is the volume you use in the actual titration. So you know maybe the volume, and that's it. So that's where we use stoichiometry to help us figure out, kind of the missing piece of information. And we could do that because we have that known solution that we know everything about. So for example, if I have a known solution, which I know the molarity and say the volume that I used, and I have an unknown solution where maybe the only thing I know about it is the volume I used. From my known solution, if I have molarity and volume, what information could I get? Molarity is moles divided by liters, which means if I have the molarity and the volume, I can get the moles of my known solution. And if I have a balanced equation and use stoichiometry, I can use the moles of my known solution to get over here to the moles of my unknown solution. And now using stoichiometry, I now have the moles of the unknown solution and the volume of the unknown solution, which means lo and behold, through my titration, I can figure out the molarity of this unknown solution. So a lot of times when we do a titration, we always have one that we know really everything about, and we have one that we're trying to find something about. We use stoichiometry to relate those two things in the balanced equation so that we could do a calculation and find something like the molarity, like you will do today to figure out the molarity of your sodium hydroxide solution that you make. Any questions on that? So how do we do a titration? Well, in an acid-base titration, you have a burette, which is terribly drawn here. Much better looking right there, I guess. And the burette has a stopcock, which opens and shuts it. By the way, that is in the shut position. Parallel to the tube is in the open position. Most of the time, keep it in the shut position so the drops don't drain out. And down in like a flask or a beaker, you put something. So very commonly, like the one we're going to do today, we're going to put some sodium hydroxide up here, which is a base. And we're going to put an acid down here. And we're going to add, for example, the base of the acid. By the way, you could absolutely do a titration where you put an acid up in the burette and you add it to the base. So you could do it either way. But that's going to be sort of the setup that's going to happen. So we do a titration until we reach what is known as the equivalence point. The equivalence point is essentially the reaction is done in the acid-base reaction. And in an acid-base reaction, when you reach the equivalence point, that is the point where exactly the moles of the acid will equal the moles of the base, which is why it's considered like the reaction's over at that point. You had a certain amount of acid moles and you added just the equal amount of base moles. They basically use each other up and it's all gone. Remember that when you do a reaction of an acid and a base, you get two things. You get a salt and water, yeah? So at the equivalence point, this is pretty much what you have left over. And if you're doing a strong acid, strong base, you have a salt that's a neutral salt that's not going to do anything. And you have water, which isn't going to do anything. And that's why they are called, as we talked about in that chapter, acid-base neutralization reactions, because ultimately, when you do a strong acid, strong base, you're making water in this case. Now, the equivalence point is when the moles of the acid and base are equal to each other. It shouldn't be confused with another terminology that's sometimes used in titrations, which is the end point of the titration. The end point of the titration is pretty much what the name sounds like. It is the point where you decide, I'm done. I'm just going to stop my titration at that point. And if you do a good titration, your endpoint and your equivalence point should be pretty close to each other, because the goal is really to stop at the equivalence point. So where you lay it up should hopefully be very close, if not at the equivalence point. But how do you know when you're doing a titration, where the equivalence point is, when you should stop? You know by using an indicator. And an indicator is something that you add. For example, you're going to add today some phenolphthalein, which is an acid-base indicator. I'll give it a go. It is PENOL, phthalene, something like that. So phenolphthalein is an indicator. All acid-base indicators actually work over a pH range. So for example, phenolphthalein works over a pH range of like 8.3 to about 10. By the way, above 7 on the pH scale is basic, so it works in a basic range. And around 8.3, it's actually colorless, which is why in acidic solutions, when you add it to your acid, it should be colorless and doesn't change any color. It's actually colorless in neutral solutions as well. It actually only turns pink in basic solutions above 8.3-ish, yes? So as you go from 8.3 heading towards a pH of 10, you will gradually see some light pink to my favorite color when I did titration, super dark pink. And I was done very quickly because I just opened that thing up, dark pink, cool, I'm done. And I just move on from it. When you do a titration, typically speaking, like the ones we're going to do in class this week and next week, and in most chemistry classes that you do, if it's an acid-base titration and you're using phenolphthalein, you typically want to stop your titration when that thing turns the lightest shade of pink that you could barely see. Like you have to hold it up to like the whiteboard to kind of see the pink. That is ideally where you want to stop your titration. You usually don't want to titrate like me and have super dark pink. And unless you just want to go home really quickly and don't care about your grade, then you could titrate like me and get very, very dark pink. The reality, though, is sometimes teachers and people put way too much pressure on it has to be light pink. And there is a very small margin of like light pink to like dark pink. And this is commonly what you hear when you do a titration. You commonly hear people say, I only added 1 drop, and that thing went from colorless to super dark pink. In fact, you might say that yourself later today, or somebody near you might say that. But it's a very common thing like, hey, I don't know, I don't get it. I just had 1 drop. It was like no color, and now it's like dark pink. And there really is a reason why that happens. I won't go into super detail on that reason, but you will learn it in 200B if you're taking 200B. And I'll tell you it again if you take it with me. But what happens if you look at a titration, there's something known as a titration curve, which basically just maps out the entire titration, pH versus how much, like sodium hydroxide you're adding. And if you look at the equivalence point in this titration, it would be perhaps somewhere around there. Now, what happens as you get close to that equivalence point, this is pH over here. The pH, as you go and get close to that equivalence point, it actually goes pretty vertical. Yeah, so the pH kind of goes vertically straight up. That means that the pH, as you get near the equivalence point, changes a lot, yeah, because it's going vertical. So the pH from here to here is a very big change in pH, yeah. Is there a very big volume difference between being here on the curve and over here on the curve or over here on the curve? The volume for all 3 of those, basically, if you just go straight down, is essentially the same. And that's why as you approach the equivalence point in these type of titrations, 1 drop is enough to actually change the pH significantly. And what that does is, because your indicator actually works on a pH range of 8.3 to 10, your 1 drop's enough to move your indicator all the way up there. And now you have a pretty dark pink solution, even though you just added like 1 drop. Now, should you dump it out and start again? The answer is not necessarily. You don't have to do that because your teacher's not mean like that, but other teachers would tell you, too dark, go do it again, right? The reason you don't have to worry about it is because if you were really careful and you missed it by 1 drop, 2 drops, 3 drops, and you're kind of really careful, if I did stop right at the equivalence point or I missed it and I'm a little bit over here, as we just mentioned, it's pretty much the same volume. You're going to be okay in your calculation because it's not that different of a volume. The reason why teachers will sometimes tell you, boy, that looks pretty dark pink, you should maybe do it again, is because they don't know if you titrate like me, which was open it up. And if I end up way over here, that is also a very high pH, right? Which means my solution over here is going to be the same dark pink as it probably is over here, right? Closer to there. The difference though is, am I near the equivalence point volume at this point? I'm way away, right? And that's why teachers will tell you sometimes that's no good, go do it again. But the truth be told is, if you are really careful as you're doing the titration and you maybe miss it by a few drops or so, in the grand scheme of things in your calculation, it's not going to make that big of a difference. It's more important when you do a number of titrations like you're going to do today and the rest of the experiment, is that the volume of sodium hydroxide that you use, for example, in each titration is a relatively the same amount in the same ballpark. So you got like 25, 24.9, 25.1, that's all the same ballpark. Not that you have like 13, 25, and 36, that's like all over the place, and that's not going to be good. So I would focus in on later today, just making sure you could try your best to try to get a light pink, but I would be more concerned with, did all my trials have relatively the same amount of sodium hydroxide, and then you'll be okay. How could you get a light pink if you're really getting close? As you're doing this titration, for example, you'll see the pink come, and then the pink will go as you kind of stir it. Pink will come, it will go, pink will come, it'll go, pink will come, it'll stay a little bit longer, then go. Pink will come and stay in a little longer. You got to give it a little bit more kind of swirling and it will go away. That's an indication that you're getting closer and closer probably to the equivalence point. So what you could actually do is, if you feel you're really close and 1 drop's going to kind of send you over the edge there in terms of the color, you could do what is sometimes referred to as adding a half a drop. And what that means is you open up your burette and just let a drop of like the sodium hydroxide form. You then take like your wash bottle that has some deionized water and you wash it in, kind of dilute the drop. And that oftentimes will help you kind of maybe get not at so dark of a pink because you're kind of diluting it in there. The good news about deionized water is you can put as much in there as you want. It will not affect the pH or the titration unless you like fill it to the brim. But you could add a little extra deionized water in your titrations. It really won't have any effect on it. Any questions on any of that there? Yeah. All right. There's that. So let's take a look at a titration problem. And really, as I mentioned before, a titration problem is really just a solution stoichiometry problem. It is still a solution stoichiometry problem or a stoichiometry problem. And when you're dealing with solution stoichiometry like titration problems, believe it or not, if it is a basic stoichiometry problem, which means it's not a limiting reagent problem, which you could have in a sort of solution stoichiometry situation, you still follow the same 4 steps. You're still going to balance the equation. You're going to convert to moles. You're going to do your mole to mole relationship. And you're going to do some moles to some other unit. So what makes it different than what we did previously? Since we're dealing with solutions, we're dealing with not grams and molar mass, but we're dealing with molarity and volume. And that means that we will be using molarity equation or formula a lot when you do these things. Most of the time right here, instead of doing grams to moles, which you still could in some type of titration, not really titration problem, more of a solution stoichiometry problem, you oftentimes will be solving for moles, which is liters times molarity, where here you definitely want that in liters. And that's a very common step there. Again, instead of grams of molar mass, volume and molarity to get the moles. Also, on the back end of the calculation, at the very end, instead of going like moles to grams, we oftentimes will have moles, and maybe we will have the volume, and we will get the molarity. So we'll use the stoichiometry to do the moles part of it, and we have the volume, we could calculate the molarity. The other thing commonly as well is sometimes you will figure out the volume at the end. So maybe you'll do moles and you have the molarity at the end, and you could figure out the liters, which would be moles divided by the molarity. So those are two common sort of endings in a stoichiometry problem that involves solutions, and definitely in titration problems. I would say calculating molarity on the back end, or volume as well, is two very common ways to end. So really all the steps are the same. The only difference, like I said, is probably using molarity on that second step and that fourth step, and you'll solve it pretty similar. So let's take a look at this one here. What volume of 1.42 molar sodium hydroxide is required to titrate 25 milliliters of a 4.5 molar sulfuric acid solution? So this one actually says titrate in here in the actual problem. I will say sometimes in word problems, they will say something like how much to neutralize it, and instead of saying titration. So it's kind of the same idea. So here we're going to do our 4 steps, which is we want to balance the equation. So again, here we're going to take all our sulfuric acid. We're going to react it with some sodium hydroxide. Again, this is an acid base and double displacement reaction. We're going to get our water from those two guys right there as they come together. And we're going to get our salt, which are these two guys coming together. Remember that we do want to put it together properly, which means sodium is +1, sulfate is -2. That gives us Na2SO4 as our salt here in our water. Any questions on that? So once we have the equation, we could look at it and kind of see what type of stoichiometry problem we got going on there. And apparently erase the N there, so put my N back in. So if we pull out the information here, we're looking for the volume of sodium hydroxide. We do know the molarity of it, which is 1.42 molar. And that again is the same as 1.42 moles per liter. For the sulfuric acid, we know the volume, 25 milliliters. We know the molarity of 4.5 molar, which again is 4.5 moles per liter. So the first thing that we could really identify in this problem is it is not a limiting reagent situation here, because I could only get 2 moles of one thing, which if you're not sure which thing that is, that's this thing we could get to moles of. We don't have enough information here to get to moles of that guy, right? So this is just a basic stoichiometry problem that we're going to do. So we have the equation. We need to make sure it's balanced, which it is not. So I need to lay up a 2 there to balance it. And I think I need to lay up a 2 right about there to balance it as well. So once we balance the equation, we're going to convert to moles. And in this case, as I just mentioned, it's really the sulfuric acid is the only thing that I can convert into moles. So if we do that, I'm going to take my volume here, and I do want to convert it into liters. So you can either divide it by 1,000 milliliters and convert it to liters, or you could just move the decimal place 3 places to the left, and it will get you 0.02500 liters. So I'm going to take that 0.02500 liters. I'm going to take the molarity of my acid, and I'm going to use it like this, where I can see both units as we've been talking about, getting rid of the big M. So I'm going to use that here as my molarity, 4.5 moles per liter of H2SO4. If I do that, that will get me 0.025 times 4.5. going to get me 0.1125 moles of my sulfuric acid. First off, any questions on that so far? So again, that's sort of the difference here. No grams, no molar mass, volume, molarity gets us the moles here. Now, we do want to think about what we're trying to find, and we are trying to find the volume here of sodium hydroxide. We do have the molarity of sodium hydroxide, which is our moles per liter. So we do have the molarity. We're looking to solve for the volume. That means that the one thing we're actually missing to basically solve this problem is the moles of the sodium hydroxide. And this is really where the stoichiometry part comes into play. We can use stoichiometry to go from moles of the acid, which we just calculated, to moles of the base. And we could do that from the balanced equation. So that is the third step, which is your mole to mole relationship. And in this case, we're interested in the sulfuric acid to the sodium hydroxide. And we can see from the equation, for every 1 mole of sulfuric acid, you get 2 moles of sodium hydroxide. So that is what we're going to use to convert us into sodium hydroxide moles. So we'll do the 1 mole of sulfuric acid, the stoichiometry, and the 2 moles of sodium hydroxide. That's going to cancel out our moles of sulfuric acid at this point. We're basically just going to multiply it by 2, and this gives me a 0.225 moles of sodium hydroxide. Any questions on that there? Again, the reason we want to do that is we now have the missing piece to our puzzle here of solving for the volume of sodium hydroxide. We now have the moles of sodium hydroxide. In the problem, they gave us the molarity of the sodium hydroxide. So we could just use the molarity equation here to figure out the volume of sodium hydroxide. So the molarity is our moles per liter. That means that the liters would equal our moles divided by the molarity. Again, here, I'm going to use the molarity in this version, and I'm going to do it more like a dimensional analysis problem so I can see the units canceling. So I'm going to take my 0.225 moles of sodium hydroxide. I'm going to use my molarity of the sodium hydroxide as a conversion factor. This, again, is where you don't have to worry about rearranging the equation. All you have to remember is opposites, which means that mole needs to go on the bottom to cancel. 1.420 moles per liter of sodium hydroxide. The moles cancel. Now we know when we set something up like that, we're dividing, which gives us the right math to do. And that will give us here 1.420. That's going to give us a 0.158 liters of sodium hydroxide, or if you want milliliters, 158 milliliters of sodium hydroxide. So hopefully you can see it is really the same 4 steps, except that in step number 2, a lot of times we'll use molarity and volume. And in the last step, we'll also integrate sort of molarity into the calculation as well. Any questions on any of those steps? By the way, if you chose to use the dilution equation for this one, you would be off on your answer because it's not a one-to-one relationship. Hence, again, why you shouldn't use M1V1 equals M2V2. Plus, if you want all the credit, you need to show all the work, and that's not showing the work. Yes, so make sure you don't use it in this situation. Any questions on that? No? All right, so once you try this one, see what you end up with. What volume of 0.15 molar phosphoric acid is needed to neutralize 45 milliliters of 0.55 molar potassium hydroxide? Okay, let's take a look at it since we're getting to the end here. Once again, this is a titration type problem. Sometimes in word problems, like I said before, they'll just call it like how much acid you need to neutralize the base or vice versa. So, you know, you can kind of think of it as a titration problem, which is really just a solution stoichiometry problem. So we need to start with our equation. So we're going to take our acid here, which is our phosphoric acid, going to react it with potassium hydroxide, which is our base. Once again, we're going to do a double switch there. And that's going to give us our water on the other side. And again, we want to make sure we put it together correctly. So K is Ka plus. Phosphate has a -3 charge. So you are going to need 3 Ks there to balance it out to 0 to get the proper formula. Now that we do have the proper formula here, we also want to make sure it's balanced. So I'm going to go with a 3 there and perhaps a 3 there. And I think we should be balanced at this point. Any questions on the equation there? All right, again, now that we have the equation, now that it's balanced, we definitely just want to kind of see what we got going on here. So in this case, we're looking for the volume of this guy, and we do have its molarity of 0.15 moles per liter. So since we are looking for the volume here, much like the last one, we do have the molarity. We are eventually going to need to get to the moles of that guy to be able to solve for it. For the KOH, we have the volume and we have the molarity. So once again, in this case, this is really the only thing that we could get to moles of, and it's not a limiting reagent problem, just a basic stoichiometry problem. So we'll start like normal, which is we want to convert to moles. We're going to divide by 1,000 or move our decimal point for our volume to get to 0.045 liters. Again, 45 divided by 1,000 basically. We're going to use our molarity here with both units showing, so 0.550 moles per liter of our KOH. The liters here are going to cancel. That's going to get us, looks like 0.045 times 0.550, going to give us 0.02475 moles of KOH. Again, we're really not interested in KOH. We need to get ourselves over here to phosphoric acid so that we ultimately could get the moles of it and solve the problem that we're looking for. So again, this is where the stoichiometry part comes into play. And from the equation, we could see that for 1 mole of phosphoric acid, you're going to get there 3 moles of KOH. So that's going to be our conversion factor. And really our next step, again, opposites cancel. So we actually need the 3 moles of KOH on the bottom and the 1 mole of phosphoric acid up on top. Those are going to cancel. So we're basically just going to divide it by 3. And that's going to get us here 0.00825 moles of our phosphoric acid. Again, we balanced the equation, we converted to moles, we did our stoichiometry and our mole to mole relationship. The last thing to do here is, in this case, we're going to use the molarity that was given to us, and now the moles that we just got to figure out the volume. So again, molarity is moles per liter. Liters is going to be moles divided by molarity. So our liters in this case would be our moles, 0.00825. Once again, taking a dimensional analysis approach with our molarity, I'm going to use it like this and flip it upside down with the moles on the bottom opposite so it cancels. And that's going to get me there. Looks like 0.055 liters, which if I multiply that by 1,000 is about 55 milliliters here of our phosphoric acid. Any questions on that one there? And perfect. All right, so we will lay it up there for today, I think.